let's talk about a totally new kind of computing. I mean, what if every single calculation a computer made could be mathematically proven to be correct, all without ever revealing any secret data? For a long time, this was just a really niche idea, pretty much stuck in the world of blockchain. But now, it's breaking out and it's about to change, well, pretty much everything. So let's dive into this idea of the trusted CPU.
All right, here's our game plan. We're going to start with the basic promise of these cryptographic proofs. Then, we'll look at the huge headache developers used to face. After that, we'll get to the big breakthrough, the trusted CPU. We'll even peek inside to see how it works. And finally, we'll talk about what a future built on this kind of trust could actually look like.
Okay, so the heart of this entire revolution is a concept called a zero-knowledge proof, or zkP for short. And honestly, the name says it all. It's a way you can prove you know something or that you did something correctly without actually revealing the secret information itself.
Let's make this real. Imagine a server somewhere out on the cloud, or hey, even your own phone runs a program. When it's done, it just hands you this tiny little cryptographic receipt. And that receipt is a mathematical guarantee that the program ran exactly as it was supposed to and got the right result. You'd never have to look over its shoulder, you just know. That's the core idea here.
Now, these proofs basically have three superpowers that make them feel like magic. First up is completeness. This just means that if something is true, you can always prove it, no problem. Then there's soundness, which is the flip side. It guarantees that a liar can't fake a proof for something that's false. And finally, the secret sauce, zero knowledge, which makes sure that no private data, no secrets are ever leaked during this whole process.
So, you're probably thinking, if this tech is so amazing, why isn't it everywhere, right? Well, for the longest time, turning this cryptographic magic into a real app was just a nightmare for developers. It came with some really big trade-offs. Developers were basically stuck between a rock and a hard place. On one hand, you had zk snarks. They're awesome because the proofs are super small and fast. But, and it's a big but, they need what's called a trusted setup. Think of it like a secret key ceremony. If that initial secret ever gets compromised, the whole system is broken. On the other side, you've got zk starks. They don't need that risky ceremony, so they're way more transparent, plus they're secure against future quantum computers. The catch? The proofs are much bigger and slower to create. So, what do?
But honestly, here was the real killer. The thing that stopped this from going mainstream. No matter which proof system you picked, you couldn't just use normal programming languages like Rust or C++. You had to learn a totally new, super specialized, and really complex language just to get anything done. I mean, imagine being an expert developer and being told you have to throw out your tools and start from scratch. It was a massive barrier.
But what if you could just get rid of that barrier? What if you could build a bridge that lets any developer, using the languages they already know and love, tap into the power of zero-knowledge proofs? Well, that is exactly what the general-purpose zkVM does. It's the breakthrough we were all waiting for.
And this is where companies like RISC come into the picture. They looked at this whole mess and asked a really smart question. Why are we forcing developers to change? Instead, let's bring this powerful zk technology to them. Their whole mission is to let developers keep using their favorite tools and just add this layer of verifiable trust on top.
And that brings us to the zkVM, the zero-knowledge virtual machine. The best way to think about it is as a mathematical computer, or what we're calling the trusted CPU. It runs normal programs, just like any computer, but with one huge difference. When it's finished, it spits out that cryptographic proof we talked about, guaranteeing the execution was perfect. It is, by its very design, a computer that cannot lie.
Okay, so how on earth does this actually work? It sounds incredibly complicated, right? But what's so beautiful about it is that from a developer's point of view, it's actually super straightforward. So let's pop the hood and see how a regular piece of code turns into a verifiable receipt.
This maps out the whole process. A developer writes their program in a totally standard language like Rust. That code gets compiled into a binary, the normal way. Then you just feed that binary into the zkVM. The zkVM runs the program, and while it's running, it generates the proof and then bundles it all up into a final receipt. The most important part, no weird zk languages, no rewriting your logic from scratch. It just works.
So what's the magic inside? Well, the RISC-0 zkVM is so clever because it combines two powerful open technologies. First, it's built on something called RISC-V, which is like a universal open-source blueprint for how a CPU should work. Because it's a standard, lots of languages like Rust and C++ already know how to talk to it. And second, it uses those zk starks for the crypto part, giving it that super transparent, future-proof security we were talking about earlier.
And what you get at the very end is this thing called a receipt.
It's got two simple parts. You've got the journal, which holds the public results of your program, basically the answer you want to share with the world. And then you have the seal. That's the ZK proof itself. It contains zero secret data, but it's the mathematical guarantee that the results in the journal are 100% correct. Anyone can take this receipt and verify it in a split second.
Okay, so we've got this incredible new tool, a way to run pretty much any program and get an ironclad mathematical guarantee it ran correctly. This is where we need to zoom out and ask the big question. What does this actually mean for all of us, for the future of, well, everything digital?
Look, the most important thing to understand is this. Even though this technology was born in the world of crypto and blockchain, its potential is so much bigger than that. We are talking about a fundamental new building block for the entire internet.
I mean, just let your imagination run with this. You could have AI models that prove they gave you an answer without any hidden bias. You could have banks sharing private data to detect fraud without ever actually showing each other the data. We could build online games that are provably, mathematically fair. Or how about digital voting systems where every single vote is verifiably counted, all while keeping it anonymous? This isn't just one thing, it's a new foundation for trust online.
And that really just leaves us with one final mind-bending question. For decades, we've had to just trust that computers were doing what we told them to. Now, for the first time in history, we don't have to trust, we can verify. So if any program can prove itself, what can we build now that was simply impossible before?